In section 7.5, we're going to be solving trigonometric equations. Our objective is to solve trigonometric equations using both algebraic and graphical techniques. Quick review: what are the main general approaches and tools we can take or use when solving equations? We're going to be able to rearrange the equations, moving terms from one side to the other and so on. Sometimes the goal is to get the variable by itself. Sometimes it's to get it equal to 0, etc. We're going to need to use some inverse functions. Once you do have an equation by itself, you'll often want to apply the inverse to get rid of that function and therefore solve for the variable. And we might have some algebraic techniques to use that include factoring or common denominators. And we may also need to employ some of our trigonometric identities. When we're solving trigonometric equations, first off, what counts as a trigonometric equation? It's going to be any equation that contains a variable inside of a trig function. So any equation that has a variable that's somewhere inside any of our trig functions. What is the end product of solving such an equation? Solving a trigonometric equation is going to result in an angle. And that angle is going to be in degrees or radians. And that's going to depend on the context. So in radians or degrees, we're going to assume we're working in radians unless otherwise mentioned. All right, so let's go ahead and look at example 1. We want to solve the equation cosine of x is equal to the square root of 3 over 2. And we're going to find all solutions. Now, the cosine of x is by itself. There's no x later on in any other portion. So we're ready actually to use the inverse function, the arc cosine function of both sides here. And that's going to eliminate the cosine function and would give us that x is equal to the arc cosine of the square root of 3 over 2. Now, when I said find all solutions, what I have in the back of my mind here is that, for example, if I was solving something like x squared equals 9, I would know that I needed to take the square root of both sides, and I would get x is equal to positive and negative 3. And there's nothing about doing the square root of both sides that tells me that I'm going to get multiple solutions, positive and negative. It's something that I have to remember to do when I take a plus and a minus. So I wanted to get that in our mind as I'm thinking about what the answer to x equals the arc cosine of the square root of 3 is. The square root of 9 itself is just 3, but by applying the square root to both sides, I have to insert plus and minus myself. So I have to find the additional solutions myself. So let's draw a unit circle and consider where cosine is equal to the square root of 3 over 2. That is one of our special ratios, and we know that that is going to occur here at the angle pi 6th, whose coordinates would be square root of 3 over 2, comma 1/2. So the cosine value is square root of 3 over 2. But that's not the only angle whose cosine is going to be square root of 3 over 2. Cosine deals with the x coordinate, so that's going to happen down here as well. That same x coordinate, we're going to have the angle in the fourth quadrant that matches this angle. My circle wasn't quite perfect circle, so it looks a little skewed right there, but hopefully that matches up. So we have this angle right here of pi sixths, and we need to have the measure of this angle as well. This angle can be measured as 11 pi sixths, right? Because this here is 0 or 2 pi, and 2 pi minus pi over 6 is 11 pi over 6. But I also could take each of these angles and wrap around. So my pi sixth, I could go back around to that angle, and I could say pi sixth is the same as 13 pi over 6. Okay, so I've got pi sixth, I've got 11 pi sixth, I've got 13 pi over 6. I also could take this angle and go backwards to it and get negative pi sixths, etc. So there are many ways of writing down each of these angles. So we're going to go with, if we're looking for all solutions, we're going to go with a pattern. And we're going to say that there are two main angles. The simplest way to write the first angle is going to be pi sixths. So we can have our angle of pi sixth, and we can add on 2 pi times k for any number of revolutions around to this angle. Then we also could take the second angle, whose simplest positive representation is the 11 pi sixths. We can take this angle, 11 pi sixths, and we can add 2 pi k to it as well. Since k is an integer, it can be positive or negative. So the positive angle would add 2 pi and be, what's 12 plus 11? That would be 23 pi sixths, which would be the next positive iteration of this one. Or k could be negative, and that would give us the negative pi sixths. So all of my solutions are solutions of these two forms. Now, it is possible to write these in one line if I wanted to, because this angle of positive pi sixths matches up with this angle that also could be called negative pi sixths. So I could write these as 2 pi k plus or minus pi sixths as just one potential way of rewriting this in one line versus in two. The difference being that this uses the positive orientation on the angle and rotates around from both. This one takes our 2 pi line and says I'm going to add in a positive or subtract off a negative, again with multiple rotations. So there's two different ways to express the angle. Doesn't matter which of the two we use. I'm going to typically go for the first notation when I present things, because we're going to be focused in a lot of these contexts about getting our angles in their positive notation. Now, if we're not given restrictions on a function, all trig equations are going to have infinitely many solutions, since there are many ways to spin around this triangle and land on an angle that is coterminal with another angle that's going to have the same sine or cosine value, whatever the trig function happens to be. So for some of these questions, we're asked to solve them just within the interval 0 to 2 pi. That's going to mean no extra spins or no extra revolutions, but I will still need to find all solutions within one positive circle. So let's take a look at the next one. Here, we need to solve sine of x plus 3 equals 2.0816. So we'll need to get our sine of x by itself. So let's start by subtracting 3 from both sides. We're going to end up with sine of x equals, we're going to take 2.0816 minus 3. It gives us sine of x equals negative 0.9184. Now, this is obviously not a known angle like the square root of 3 over 2 was in the last question. We're still going to be able to approximate its position on a unit circle. We know that on the unit circle down here would be negative 1 for the y value. So if the sine value, which is the y coordinate, is negative 0.9, it's quite low. And so our angle would be something like here or here. So we're going to have an angle that's going to be one of these two. I don't know what it is, so I will need to use the arc sine function in order to find that. So x is equal to the arc sine of negative 0.9184. Since we need to know that angle in a decimal, let's type it in. We need to do the arc sine or inverse sine of negative 0.9184. And what that gives me is the angle negative 1.164. Remember that arc sine has a range from negative pi halves to pi halves. So the angle in quadrant 4 is the angle that is initially returned. So that is this negative angle right here. The other angle that we need to find is going to have a reference angle that is the same size. So it's going to be past the angle pi by a measure of 1.164. So this next angle right here is going to be at pi plus 1.164. So if we take pi plus 1.164, that ends us at the angle 4.3056. I was really rounding this to 4 places, even though I didn't write down the 0. It was my intention to keep 4 places, so I've still got my 4 places there on the 4.3056. Okay, so that's my angle. So one of my answers for x is 4.3056, and the other one, remember we got this angle right here, but that is the negative orientation for this angle, and I need both of my answers to be framed in terms of their positive orientation. So I need to look at the angle here instead of here. To find that angle, I need to find out the angle that is short from 2 pi by a measure of 1.164. So I need to take 2 pi minus the 1.164. So this angle is going to be about 5.1192. So the next answer is the angle 5.1192 in radians. These are the two distinct angles, angle 1 right here and angle 2 right here, in their positive radian measure. They are between 0 and 2 pi. So neither of those is actually the one that comes out when you enter the arc sine statement. That's interesting to note because the arc sine statement returned the negative angle, and we had to compensate for that by making it a positive angle and then finding its matching matching angle to make it in quadrant 3 as well as that quadrant 4 angle in positive notation. So definitely some unit circle notation coming in with the arc trig functions here. Let's continue and look at the next example. Okay, in example 3, we need to solve cosine squared x plus 2 cosine x equals 3. Again, it's important to note that I am looking for solutions that are just within the 0 to 2 pi, so I don't need to worry about rotating multiple circles. And I noticed this one's quadratic because it's got a cosine squared and a cosine. So let's get this equal to 0. Cosine squared x plus 2 cosine x minus 3 equals 0. And I'm going to be able to factor this. So I'm going to factor this into cosine x. We need cosine x. And then I need to multiply to 3 and add to 2. So we're going to use 3 and 1. I need it to be a positive 3 and a negative 1 so that those add to a positive 2 and multiply to a negative 3. Then we're going to set each factor equal to 0. So cosine x plus 3 equals 0 and cosine x minus 1 equals 0. If we subtract the 3 over, cosine x is equal to negative 3. If we add the 1, cosine x is equal to positive 1. So to solve for x, we're going to need to take the inverse cosine of both sides. So we'll apply the arc cosine of negative 3 and the arc cosine of 1. On the arc cosine of negative 3 side, we've got ourselves a unit circle. In a unit circle, we know that this goes from negative 1 to 1. So negative 3, off my page probably here, isn't going to fit on this circle. So this one is going to be undefined, which means it's not possible for x to equal the arc cosine of negative 3. We don't get a solution from that side. If we don't get a solution from either side, we'll say that our equation has no solution. But if we look at this side, it is possible for the arc cosine of 1 to be evaluated. My cosine value needs to be 1. That's going to happen exactly once right here. Over here, it would have been a negative 1, not a positive 1. And there's no other place where cosine, which is the x coordinate, is going to be exactly 1. So that's going to happen at this angle, which is the angle 0, or 2 pi, or 4 pi, etc. Notice that we want answers that are in between 0 and 2 pi, including 0 but not including 2 pi, so no duplicates. So my answer is going to be x equals 0 as the simplest positive measure for that angle. Technically, it's not positive, it's 0, but it's the simplest measure for that angle. So x equals 0. I am asked to find both graphical and numerical solutions, or graphical and algebraic solutions. So we're going to graph this function as well. And I'm going to start graphing it when it's equal to 0. I'm going to write this side as a function. So f of x equals cosine squared of x plus 2 cosine of x minus 3. And I actually only want to see this between 0 and 2 pi. And let's go ahead and look at our solutions here. We have a solution here at 0, and the next one is at 2 pi, but we're not looking at 2 pi as included in this interval. So the only solution we have listed where it is equal to 0 is x equals 0. So we've seen their graphical solution. There are lots and lots more solutions, but they are at all multiples of 2 pi. So if we were looking for all solutions, we would say k2 pi. Okay, we've got one more to take a look at. In example 4, we're going to solve cosine of pi minus x plus sine of x minus pi halves equals 1 in this interval using both graphical and algebraic techniques. Okay. Cosine of pi minus x plus sine of x minus pi halves equals 1. In this one, we are going to need to use some identities. It looks like I can use the sum and difference identities for sine and cosine here. So let me locate those. You can find these identities in your formula sheets or earlier in your notes. We're going to need to use the difference identity for cosine and the sum identity for sine. So starting with cosine, the difference identity for cosine of u minus v is going to be cosine u cosine v. So cosine pi cosine x. For the difference identity, it's going to be plus, and then sine u sine v. So sine pi sine x. That portion is going to correspond with the difference of cosine. And now we're going to do the sum or difference. It's the difference again for sine. It's going to be sine u cosine v minus cosine u sine v. Let's write this one in. We're going to have plus sine x cosine pi halves minus cosine x sine pi halves. And it's still going to be equal to 1. So this portion is the sine difference identity with these two terms. We are able to evaluate the cosine of pi, the sine of pi, the cosine of pi halves, and the sine of pi halves. So we're going to evaluate each of those numerically. We know that the cosine of pi, that's over here, and this is the ordered pair -1, 0. That's going to be a -1 times the cosine of x plus the sine of pi, which is 0. So 0 times the sine of x, that's going to just turn into 0, plus the sine of x times the cosine of pi halves. This is 0, 1. So the cosine value is 0. And then minus the cosine x times the sine of pi halves, which is 1. So I end up with negative cosine x plus 0 minus cosine x equals 1. That these are like terms, so negative cosine x minus cosine x combines to -2 cosine x equals 1. We can divide off the -2, so cosine of x is equal to -1/2. Now we're able to apply the arc cosine, the inverse cosine, to both sides. And x is going to be equal to the arc cosine of -1/2. And when we use the unit circle here, (1/2) is going to refer to one of our special angles. So we're going to need to have the angle that has the taller and shorter side. So this is going to be the angle. So remember, arc cosine is going to return things that are between 0 and pi. This is the output of arc cosine. And this angle is going to be, let's see, if it was positive, I would have gotten pi over 3. Since it's negative, I'm going to get 2 pi over 3. And the ordered pair right here is going to be -1/2 square root of 3 over 2. The other value that would have the same cosine would be on the bottom there in quadrant 3. And it's going to have the same reference angle. So remember that 2 pi over 3 is this full angle. The reference angle on this is pi over 3. That's the angle on the inside. And so this angle down here is pi over 3 more than pi. So 1 pi plus pi over 3 is going to be 4 pi over 3. You can also look this up on your unit circle. So that angle down here is 4 pi over 3. So my answers are x equals 2 pi over 3 and x equals 4 pi over 3. And I only want answers. Oh, you know what? I'm mistaken. I apologize. These are answers in the interval 0 to 2 pi, which is the typical interval that we solve. I just didn't realize we're solving a different interval here. So now we're solving between negative pi and pi. So between negative pi and pi, we're just going to reframe these. Remember that this is pi in this direction, and this is negative pi in this direction. So I actually want the positive orientation for this angle. So this one is still good, but I want the negative orientation for this one. And so this is negative 2 pi over 3. So again, this is an atypical way to phrase it, but I can say I want my angles phrased as plus and minus 2 pi over 3. Those are the two answers in the interval negative pi to positive pi. It is still one full circle. It's just not a full circle that starts on the positive x-axis. It's a full circle that slices around from the negative x-axis. Not a standard way to answer the question, but it is definitely a way that the question could be answered. And it does allow me to answer with positive and negative. It worked out to be positive and negative of the same angle in this context. So I'm going to leave my answers written both ways. This way is more standard for this kind of question, but when asked to do a different way of phrasing, I certainly can find a different angle that is coterminal with the one I previously found.